In order to guarantee full understanding of this course, you should have completed previous universal molding modules. MU1 Introduction, MU2 Fundamentals, MU3 Molding with Graphs, MU4 Material Morphology, MU5 Press Calculations, MU6 Injection Unit Calculations, MU7 Cooling Calculations, MU8 Rheology. Remember that your objective should be to identify the requirements of your process and attend those needs with well-thought-out solutions. Universal molding is a discipline that promotes a structure of organized events. Determining injection speed. Once again, remember that before performing a universal molding laboratory, you have to do molding from the desk. All auxiliary equipment should be properly installed and correctly operating. Temperatures, water temperature, injection barrel temperature profile, and its corresponding melt temperatures, heat zones if the mold has hot runners, etc., should already be reached. Barrel adjustments, recovery and transfer positions, decompression, recovery speed, etc., should have been programmed. The proper nozzle tip should have been installed. The required closing force should have been set. The platen openings, their movement, speeds, and mold protection should have been carefully and precisely adjusted. Extended cooling time should have been set. Remember that cooling time is set higher than required in order not to interfere in the determination of the other previously adjusted parameters. Cooling time will be optimized at the end. Important: the equipment should only be operated and/or adjusted by qualified personnel who have read the operational manuals of the equipment and have mastered the equipment's functionality. In this course, we will discuss understanding fill and its limitations, determining minimum injection time and injection pressure limit, determining injection time and injection speed, rheology graph and determining ideal injection time and injection speed, approximated graph. Laboratory 1. Understanding fill and its limitations, determining minimum injection time and injection pressure limit. The objective of this laboratory is to understand the fill's behavior, determining how fast the mold can be filled without causing defects. Here we determine the maximum speed or minimum injection time and identify limitations such as material degradation or burning as a consequence of excess speed. For example, rigid PVC tends to burn if the injection speed is high. Vent problems such as burns can occur due to gas combustion or dieseling. This defect can be corrected by cleaning the vents or, in the worst case, repairing or modifying the mold. Equipment limitations, such as an injection unit that is incapable of reaching high injection speeds, which can be the consequence of an injection unit that is inadequate for the mold, etc.
What happens if some equipment limitation or defect appears, such as limited injection speed?
If the limitation requires a modification or simple change in equipment, then do it. However, if the modification or the change is not viable, or if it is not economically sustainable, you will have to run the laboratory with the equipment you have. In the case of limited injection speed, it would be best to change to an appropriate injection unit. If this is economically prohibitive, you'll have to work with a limited injection speed.
Will all programmed injection speeds, whether slow or fast, be reached by the injection unit?
Not necessarily. The programmed velocity could be limited by an inadequate injection unit, for example, due to a low percentage of utilization. Let me explain. Recovery of 10 cubic centimeters in a unit with a recovery capacity of 100 cubic centimeters, or 10% of utilization, might not have the acceleration displacement required to reach the set speed. Always verify that the set speed is being reached. A. Verify that the transfer position from injection to pack was entered. Do you remember how? This procedure was explained in injection unit calculations. With machines up to 400 metric tons, if percentage of utilization is 35% or less, use 6 millimeters. 65% or more, use 12 millimeters. And between 35% and 65%, interpolate. With machines 400 metric tons or larger, if percentage of utilization is 35% or less, use 12 millimeters. If it's 65% or more, use 25 millimeters. If it's between 35% and 65%, interpolate. B. Turn off the pack stage so that you don't have problems determining the minimum injection time. You can do this by adjusting the pack time and/or pressure to 0. Some injection machines come with pack time divided into pack and hold. Turn off one of these. C. Adjust the injection unit to produce parts that are 20% incomplete. This is done to avoid damage to the mold, to the machine, or to both. Recovery position equals transfer position plus 80% of injection displacement. Note: it's important to maintain a cooling time that is larger than required while determining the minimum injection time. You should also be alert while the mold closes, so that the mold doesn't close with unreleased parts. Turn off any alarms that could stop the laboratory, such as the alarm that limits the maximum injection time. D. Find the minimum injection time and maximum injection speed for the mold being used. The idea is to increase the injection speed until the injection time stops significantly decreasing. A safe and practical method is to increase the injection velocity and injection limit pressure together until the injection time stops decreasing. Be careful. Although easier, do not adjust the limit pressure to the maximum. It could cause breakage. During the experiment, verify that parts don't remain trapped in the cavities. You probably will have to do this step with the control on semi-automatic. If you turned off the pack stage by adjusting the pack time to 0, verify the demolding. If the parts are too hot when demolded, increase the cooling time until the parts demold at a lower temperature. It's recommended doing this experiment with a graph of injection time versus injection pressure or injection speed, which will help you determine the minimum injection time. Let's see. The graph of injection time versus injection speed illustrates how, at 92 millimeters per second, the decrease in time becomes insignificant. E. Though the parts will be incomplete, make sure you obtain parts that are free of defects due to degradation.
What happens if the parts show defects due to degradation?
If the limitation requires a simple mold repair, do it and repeat the exercise. However, if the repair is not viable or economically acceptable, the speed at which the defect appeared should be your maximum speed. Notice, the part's volume increases with an increase in injection speed. This is a normal effect that won't affect the experiment. Slowly filling produces incomplete parts, and rapidly filling will produce parts that seem to be totally full.
If the recovery position is set to 80% of the fill, how is it that the weight of the parts increases with the increase in speed?
Remember that at the end of injection, the transfer position, the plastic in front of the check ring is what stops the screw. The screw, as well as the plastic, continues traveling with its own kinetic energy. In other words, the melt will continue to fill the mold until all that energy in the form of speed is consumed. Because of this, the higher the injection speed, the higher the energy at the moment of transfer, and consequently, the more fill volume there will be. Continue determining the minimum injection time. F. Note the maximum pressure and the maximum speed obtained. Vmax equals maximum speed, a machine parameter. pH max equals maximum hydraulic pressure, a machine parameter. If you're working with universal parameters, it will be F max equals maximum flow, PP max equals maximum plastic pressure. Summary of the steps. Laboratory 1. Understanding fill and its limitations, determining minimum injection time and injection pressure limit. A. Adjust the transfer position from injection to pack. B. Turn off the pack stage so that it doesn't interfere with the determination of the injection time. C. Adjust the injection unit to produce parts that are 20% incomplete. Recovery position equals transfer position plus 80% of the injection displacement. D. Find the minimum injection time and maximum injection speed for the mold being used. E. Though the parts are incomplete, make sure that they are free of defects due to degradation. F. Note the maximum pressure and the maximum speed obtained. Vmax equals maximum speed, or Fmax equals maximum flow. pH max equals maximum hydraulic pressure, or PP max equals maximum plastic pressure.
Let's review.
Laboratory 2. Determining the injection time and injection speed. A. Adjust the injection speed or speeds to 95% of the maximum velocity, or Vmax, found, and call it V95. V95 equals 0.95 times Vmax.
Should I only use one fill speed?
Previous courses explained that if the recovery and transfer positions are correctly adjusted, the majority of molds can be filled with only one injection speed. Family molds, which have cavities with distinct volumes and geometries, could require more than one speed. However, the majority of molds can be filled with only one injection speed. Do not use a speed profile if it is not necessary. B. Set the pressure limit to Pmax. C. With the speed V95, adjust the recovery position so that the mold, parts, and runner is filled to at least 95% of its total weight.
Does this mean it would probably reach the adjusted pressure limit?
It is possible that, during the experiment, it will reach the pressure limit, since Pmax was found using an incomplete mold fill of 80%. Always verify that the pressure limit is never reached. Keep it 5 to 10% above the maximum fill pressure. Notes:
Do not try to maximize the fill during the injection stage. Only guarantee close to 95%. Trying to reach the maximum could result in problems with the screw bouncing back.
Make sure you produce parts without flash. Guarantee that the pressure during injection remains at least 5% less than the set pressure limit. D. Without changing the transfer position and continuing with the pack stage turned off, pack time equals 0 and/or pack pressure equals 0, create a rheology table with distinct injection speeds. Remember that this laboratory can be performed with conventional machine rheology or by power, with either complete or approximated rheology.
Note: we universal molders prefer approximated rheology by power, since the equations represent evaluated effects.
The headings should include machine parameters, injection speed, injection time, hydraulic transfer pressure, and plastic transfer pressure. Rheology by power, flow, and power. Remember to include their corresponding units.
With rheology by power, use the following equations. Average injection flow equals injection volume divided by injection time. Injection volume equals area of the screw, diameter squared times pi divided by 4, times injection displacement. Peak power equals average injection flow times pressure at the moment of transfer. Plastic pressure equals hydraulic pressure times intensification ratio.
Each of these equations was explained in detail in MU's machine rheology course. In the velocity column, if working with approximated rheology, use the first and last rows for the laboratory. The first speed will be equal to 95% of the maximum speed found in the previous laboratory. V95 equals 0.95 times Vmax. The second and last speed will be equal to 10% of velocity V95, or 0.1 times V95. If working with complete rheology, calculate and write down 10 speed values in descending order. The first will equal velocity V95, and the next 9 will be in decrements of 0.1 times V95. E. Without turning on the pack stage and without changing the transfer position, inject at those distinct velocities, taking readings of maximum hydraulic pressure. Take the reading at the position where injection finishes. If the machine gives plastic pressure readings, then eliminate the hydraulic pressure spaces or leave them blank. Fill time. Take a reading of the time it takes from the beginning of injection to the transfer position. F. Calculate and fill the table with all corresponding values. Remember that maximum plastic pressure equals maximum hydraulic pressure times intensification ratio. If the machine gives plastic pressure readings, ignore this calculation, or assume that the intensification ratio is equal to 1. Summary of the steps. Laboratory 2. Determining the injection time and injection speed. A. Adjust the injection speed or speeds to 95% of the maximum velocity, or Vmax, found, and call it V95. V95 equals 0.95 times Vmax. B. Adjust the pressure limit to Pmax.
C. With the speed V95, adjust the recovery position so that the mold, parts, and runner is filled close to 95% of its total weight. Guarantee that the set pressure limit is at least 5% more than the maximum injection pressure.
D. Create a rheology table with distinct injection speeds. E. Without changing the transfer position and continuing with the pack stage turned off, pack time equals 0 and/or pack pressure equals 0, inject at distinct injection speeds, taking readings of maximum pressure and fill time. F. Calculate and fill the table with all corresponding values. Remember that maximum plastic pressure equals maximum hydraulic pressure times intensification ratio.
Let's review.
Laboratory 3. Rheology graph and determining ideal injection time and injection speed. A machine rheology graph is used during the selection of injection time. A. Using the completed rheology table, create a rheology graph. If working with rheology by power, your rheology table should look like this.
For machine parameters, we have columns for velocity, injection time, hydraulic transfer pressure, plastic transfer pressure, flow, and power.
And your corresponding rheology graph should look like this. According to this graph, power is no longer significantly contributing to injection time when power is greater than 1,500,000 psi times cubic inches per second. Approximated graph. As explained in the previous course, developing an injection molding rheology laboratory consumes time and resources. With approximated rheology, a mathematical prediction technique, the laboratory can be done in less than 1/3 of the time. In the previous example, we used velocity V95 and 10% of V95 to find the readings for injection time and pressure at the moment of transfer.
If we use rheology by power to calculate the corresponding values for plastic pressure, flow, and injection power, we find machine parameters for injection time, hydraulic transfer pressure, plastic transfer pressure, flow, and power.
If you work with rheology by power, you will notice that there is a relatively linear relation between injection flow and power. Using the line equation y equals y naught plus m times x, where y is flow, y naught is the intercept in the injection flow coordinate, m is the slope, and x is the injection peak power. Once m is determined, the intercept y naught is obtained by substituting one of the two known points in the line equation and solving for y naught.
The value of these constants can be found using simple mathematics or with Excel. Peak power equals 8,225 times average flow times 291,032. Knowing that the volume required by the mold is 273 cubic inches, and using the average flow equation, required volume divided by injection time, we get average flow is equal to 273 cubic inches divided by injection time. With these two equations, you can now approximate the intermediate values of the graph. With 10 equidistant injection times, between the minimum and maximum injection times, we calculate their corresponding average flows and peak injection powers. The corresponding rheological graph will look like this.
Exactly where in the graph does the power stop contributing to the injection time?
The best way to determine where the plateau begins is by using the following equation. T plateau equals T minimum plus T maximum minus T minimum divided by 9. T minimum equals injection time corresponding to maximum injection speed. T maximum equals injection time corresponding to the minimum injection speed. T plateau equals injection time where the plateau begins in the graph. The machine rheology course explained that this equation comes from the average of a group of experienced molders. Using the rheology table from the previous example, we obtain T minimum, which corresponds to the speed of 3.2 inches per second, V95, and T max, which corresponds to the speed of 0.3 inches per second, 10% of V95. Substituting T minimum equals 0.5 seconds and T maximum equals 5 seconds, we obtain T plateau equals 0.5 seconds plus 5 seconds minus 0.5 seconds divided by 9, which equals 1 second. According to this equation, the plateau begins at an injection time of 1 second. With rheology by power, 1 second will correspond to a power of 1,312,448 psi times cubic inches per second.
How do I obtain the ideal injection time?
That depends on the type of industry. Conventional molding industries can select an ideal injection time between T plateau and T minimum. T intermediate equals T plateau plus T minimum, all divided by 2. Industries that mold materials that are sensitive to the injection speed, such as those that mold rigid PVC fittings, should be close to T plateau. T for sensitive material equals T minimum plus 3/4 of T plateau minus T minimum. High injection volume industries, such as cap manufacturers, should be close to T minimum. T fast equals T minimum plus 1/4 of the difference between T plateau and T minimum. B. Select the ideal injection time for your application. Summarizing what was just explained, conventional molding industries between T minimum and T plateau. T intermediate equals T plateau plus T minimum, all divided by 2. Or substituting for T plateau and simplifying, T intermediate equals T minimum plus the difference of T max and T minimum divided by 18. Industries that mold sensitive material should be close to T plateau. T for sensitive material equals T minimum plus 3/4 of the difference between T plateau and T minimum. Or substituting for T plateau and simplifying, T for sensitive material equals T minimum plus the difference of T max and T minimum divided by 12. High volume injection industries should be close to T minimum. T fast equals T minimum plus 1/4 of the difference between T plateau and T minimum. Or substituting for T plateau and simplifying, T fast equals T minimum plus the difference between T maximum and T minimum divided by 36. After selecting the type of application, select the corresponding equation, substituting the values of T minimum and T maximum, and determining the ideal injection time. Utilizing the previous example where T minimum equals 0.5 seconds, T maximum equals 5 seconds, and T plateau equals 1 second, we obtain, for an average application, T intermediate equals T minimum plus the difference between T maximum and T minimum divided by 18. In this case, it equals 0.75 seconds. For sensitive material application, T for sensitive material equals T minimum plus the difference between T maximum and T minimum divided by 12. In this case, this equals 0.875 seconds. For a high volume application, T fast equals T minimum plus the difference between T maximum and T minimum divided by 36. In this case, this equals 0.625 seconds.
So we simply determine the ideal injection time with these equations?
These equations help standardize the selection of injection time. However, they are just a reference. C. Determine the ideal injection speed. Once injection time is determined, find the corresponding injection speed. This is done by adjusting the injection speed until it approximately equals the ideal injection time found. Once the ideal speed is found, verify that the mold fills more than 95% of its total weight, parts and runner. If not, readjust the recovery position until both the ideal injection time and a fill of at least 95% are achieved.
Can every mold be filled more than 95% in the injection stage?
Not necessarily. Some molds are designed so they cannot be filled to 95% during the injection stage, and in some cases molds must be repaired.
What happens if the determined injection speed causes burns on the molded parts?
You should take a closer look. For example, if the burns are at the end of the fill, you probably will find that the vents are plugged or defective. If the burns are around the edges or corners, they could be caused by an edge or flash of metal in the mold. If the burn forms streaks that extend along the length of the fill or from the gate, the material is probably degrading from friction or shear, etc. consult the mold maintenance department. It will probably recommend some type of maintenance or repair. Follow the recommendations and return to molding at the determined injection speed. If the recommendation isn't possible, perhaps because it is too costly, you will have to reduce the speed until the defect disappears.
If I can't use Rheology because of material limitations, example degradation, or equipment limitations, example unable to inject quickly, and I have to mold under those conditions, how do I determine injection speed and time?
Very good question. Unfortunately, not every material, mold, or molding equipment is at its best design condition. What's worse, for whatever reason, is being forced to produce with these deficiencies. Follow this simple procedure. Inject, incrementing speed until reaching the specific limitation. Then, reduce the maximum velocity found by 5% and inject with this new speed. If the defect disappears, this will become your injection speed or time. D. Note the values found for injection time, injection speed and its corresponding injection flow, transfer position and its corresponding transfer volume, plastic pressure limit, including hydraulic pressure limit if it applies, recovery position and its corresponding recovery volume. Summary of the steps. Laboratory 3. Rheology graph and determining ideal injection time and injection speed. A. Using the completed rheology table, create a graph of rheology. B. Select the ideal injection time for your application. C. Determine the ideal injection speed that corresponds to the injection time found. D. Note the values found for injection time, injection speed and its corresponding injection flow, transfer position and its corresponding transfer volume, plastic pressure limit, including hydraulic pressure limit if it applies, recovery position and its corresponding recovery volume. Notes: do not try to maximize the fill. Only guarantee a little more than 95%. Trying to reach the maximum could cause problems with the screw bouncing back. Make sure you are producing parts with no flash. Guarantee that the pressure during injection remains at least 5% less than the adjusted pressure limit. Remember that you are working with expensive equipment. Do not rush your work and follow all safety regulations established by your company and your government's agencies. You can never be too careful.
Let's review. You have completed this lesson.